Thank you very much for the introduction and for having me here. There is also some introduction here on the slide, but basically what I would like to say is I've been doing this stuff basically for almost 30 years now, Linux kernel hardening on and off, and I switched to userland and then back to kernel for this project, which isn't originally mine, actually, more about this later. And I would also like to thank CIQ, the company that enabled me to give this talk today, and enabled accelerated release for 1.0 to be done in time and with new features. They supported work by me and by another employee at CIQ. LKRG, Linux Kernel Runtime Guard, the project was founded by Zabrocki. And he actually started working on it, I don't know exactly when, some files are dated 2015, but we released together version 0 in 2018. First public release, and we decided to do it under Openwall, even though no code was written by anyone who had been with Openwall by that point. So I joined and we released Adam's code. And already at the time, Linux Kernel Runtime Guard performed runtime integrity checking of the kernel, and I think already of the models as well. And before version 0, on my suggestion, we also added integrity checking of processes or tasks. Under Linux, a task is basically a thread, so we use this notion in the kernel. Some of these the objects that LKRG protects are code. Some others are data, and there is also a third category that is neither. It's control flow, and it is blocking access to some attack surfaces of the kernel. And besides all of this integrity checking, we also have response to almost successful detected attacks. More about response later, but it can be some action LKRG takes to stop the attack. And we also have optional encrypted remote login, a fairly recent addition that I made, released publicly last year, and it was sponsored by Binarly 3 years ago. Actually, it was in released code for a while, and then CIQ also helped me put enough time into cleaning this up for release, and we did. The project isn't a very large one, it's actually a small one, I would say, but nevertheless we do have quite some contributors, and more people are testing, contributing indirectly. And the code base is also small, much smaller than maybe I would say competing solutions, but it's not exactly right. I will show some there will be a slide on the technology landscape, comparable alternatives, so to speak, for Linux, not exactly alternative, of course. And then there are commercial EDR solutions, for example, for Windows, which are much larger, and functionality, I don't know how to compare. So there is some criticism. Just yesterday, one of you asked me whether I believe in LKRG, and that guy said that he doesn't. Well, I'm not religious, and I would say that this is technology with its advantages and disadvantages. It is not perfect. It is bypassable by design, as our website said from the very start. But nevertheless, the concept, I think, can live even with defense from same privilege level. One of the precedents was in 1984. I don't know if there was anything like this earlier, but people started playing a game that is basically just like this. You have at least two tasks competing in the same address space and trying, in that case, to kill each other. In our case, the goal is actually comparably modest. We need to detect and stop the attack. Even if it just detected and logged it remotely, it's already a partial success. So we do not need to actually eliminate opponents in memory. This is more than we need for this task. And this core of war game, it's actually still active. I was a bit surprised. Just this year there was a competition, and if you look at the website, there are past competitions like months back and years back, and it's active. It's fun. Okay, so I did mention I was into this stuff or related stuff before. I started my Linux kernel security adventure with hardening patches in 97. One of them was the non-executable stack for user space processes. It was the first time non-executable memory was implemented on Linux and on x86 for user tasks. As far as I'm aware, under any operating system. There were some others like Digitals 364 for Alpha, but not x86 and not Linux. Anyway, I did this stuff. It was also a tiny project compared to today's, to JR Security, for example. And I did this stuff for quite some years. Basically, maintenance wasn't adding a lot. But even during those years, even for those Openwall patches, they evolved not only to protect user space, which they did initially, but also to add some protection to the kernel. I was already receiving some information about new kernel vulnerabilities being handled. We had our own Linux distribution, and so through vendor sec, which existed at the time, there was discussion, for example, about some race condition with file objects in the Linux kernel, and I added to Openwall patches some extra locking, for example, to preemptively protect against further attacks like this. And then JR Security appeared just a few years after my patches, initially as a fork of my patches plus PEX, and ported to Linux 2.6 before I dared to do the same. I was slow to move to new kernels. I still am slow to move to new stuff today, so that's why I basically let others proceed, and they did, and they do, and that is great. And then there were upstreaming efforts. So those kernel patches, they existed out of tree, but of course, we were asked once in a while why the stuff is not upstream. And in 2011, we finally proceeded. There is this very capable guy, Vasily, and he was on our team at Openwall, and for this year he was a student under Google Summer of Code. We got into this project, which by the way helped us quite a bit. We got as a mentoring organization, we got several students, and including Vasily, and Vasily did pretty good work. We actually got some hardening changes upstream, not a lot, but you know, it is pretty hard to get any patches upstream. You have to go through many cycles of revisions and convincing and all that. And he managed. And then there was a kernel self-protection project by Case Cook, and I think it received funding from Linux Foundation in 2015, which is why it finally started. But then I think priorities may have changed or something. It isn't so active, at least under such leadership anymore, but nevertheless resources exist and people continue with hardening. There is still this kernel hardening mailing list at Openwall, and there is also Linux hardening on the kernel infrastructure now, a separate mailing list. Where the KSPP project should be primarily be discussed, or kernel hardening in general. And a more similar solution maybe to LKRG is Tetragon, implemented through eBPF, I think 3 years ago. I actually know some people behind it, so I wrote the company name here, that's how they released, but it's some of us basically, I would say, this community. So a good project, and I do not view it as competitor or any of those for LKRG. They are mostly orthogonal and can coexist, and LKRG maybe is useful even to protect some of those. It would probably be said that GR security, the paid one, the updated one, up-to-date on up-to-date kernel does so much that maybe our poor man's protection is extraneous, but nevertheless, people do combine things. People do run all the forks of GR security. Partial trees actually cut down on newer kernels, and they do mix this with LKRG. Then, how does it do runtime integrity checking? It involves several activities. One of the steps here, it's generating a random key. It's basically part of LKRG self-protection, because otherwise, if you would find the hashes in memory, you can compute hashes of your modified code and substitute in there, and they would just work. Here you would also need to find the key, read the key, compute keyed hash, and write that. Just a little bit of extra protection. We do have other bits, not all of them mentioned in here. And then we snapshot current or initial state of whatever we will be integrity checking, including kernel and including tasks. Mostly this split, but also there's CPU registers, some of them that are global and control basically security settings of the CPU. And we track legitimate changes. Unfortunately, we cannot just have a static hash of the kernel. We started, and this is our hash, and we insist this is our only correct hash. The kernel self-modifies. And then there are tasks obviously changing, they're starting, they're stopping, they pass through set user ID calls, so credentials change, which we track and which we care about a lot. So we have to track those legitimate changes, and when we do this, we have to temporarily pause our integrity checking just of this task, if it's one task, because it would be an inconsistent state. The kernel updates the credentials, and there are several, and we need to dump the new ones as new correct ones. And there is a time window when things are inconsistent, and we have to pause. And then we update if this kernel's update is deemed successful. So, for example, a set user ID call returns success, we update our copy. And finally, we not finally, but finally on a properly functioning system without attack, we validate the current state against what we recorded. We do basically integrity checking in this way. We check integrity. We do this pretty frequently. It was Adam's idea to do this also at random events. I did mention this on another slide about protecting from same privilege level and exploits knowing what to expect, because they can see our open source project, they know exactly what it does. But there is some randomness involved, and Adam likes this very much and insists we keep it. I'm not so sure. It is worth it, because it makes performance maybe a bit unpredictable in some cases of high load or whatever. But anyway, we do have this, and most importantly, for test credentials, we check them just before they would be used, but I do have this on a separate slide. And finally, if there is a detected violation, we also log it, maybe remotely, and we trigger the configured response, which can vary, and it actually does vary by default for different kinds of violations, for good reasons, because for some violations, pretty mild response can be somewhat effective, so by default we do not insist on doing anything more dramatic. But if we determine that the kernel hash has changed unexpectedly, we do not know where in in those megabytes, something is wrong, we cannot just repair it reliably. So the default action is to panic the kernel for that. It's already successful attack, and we cannot easily recover from it and be confident it is okay. Also happens in case of rootkits. So for kernel integrity checking or system integrity checking, which is kernel plus more, that is the global state. This includes which CPUs are online or offline, and CPU here means actually logical CPU, so hyperthread or a core. And they can be going online, offline, and happens especially on power-saving devices, like if someone puts LKRG on Android, and some people did, it could be happening there pretty likely. On servers, not so common, but you can also bring CPUs offline and online, I sometimes do. And then it protects various security flags of the CPU, write protect, and the newer ones, map and smap. Protects interrupt descriptor table and some model-specific registers, including one, for example, that defines syscall entry address in the kernel. Obviously, if you change this, then you can hijack control and do a lot of things. And the kernel image in memory, models in memory are protected, and the list of models, which models exist, is also protected. So that's basically it for the basic functionality, but then there is this thing about self-modification of the kernel. It is called the feature that self-modification is for, it's called static branches. It is an optimization in the kernel. It was implemented about 15 years ago, I think, to turn some conditional branches into unconditional ones. So if there is some condition that is almost always true or almost always false in a particular runtime, you do not know this at compile time yet. In a particular runtime it is almost always true, then it can be compiled, dynamically patched to become unconditional. And when the condition reverses, it is patched again to become the opposite condition. Usually those things are done for like plugging in extra hardware devices. Do you have this device or don't you have? So you plug in and there's a kernel patch happening in the background. You do not see it, but it is. And then you unplug and there's another, for example. But there are more cases, there are lots of those static branches. So on different systems it happens sometimes very infrequently, only at boot up and shutdown maybe. And on another system can be happening every second. It does happen at Virt. So we have to adapt to this and detect this and recompute hashes at least of those regions where the change occurred. So, for example, if it occurred just in some kernel module load in memory, we compute hash of this module. And finally, there is also hooking by others, not only LKRG. There can be profiling frameworks, there can be other security solutions, there can be rootkits, and for now, somewhat controversially, we do support ftrace. We allow it, we update our state as if this is legitimate. And this is somewhat protected by our making sure kind of that this is done by legitimate root and not just someone who had just compromised a process to be root, at least for attacks through the kernel. And then we protect integrity of tasks. There is this tricky notion of objective and subjective credentials. That's terminology used inside the Linux kernel. Each task has its set of typical Unix credentials and user IDs, group IDs, set of 4 different pairs. And it also has subjective ones, which some file systems, for example, can temporarily override. This is really tricky for LKRG. And we had lots of bugs, lots of reading of kernel code to achieve alignment of what we expect and what the kernel actually does. One thing is that the override creds and revert creds calls inside the kernel that manage subjective credentials, they are not used symmetrically by the kernel. It can happen that the kernel does override twice and revert once, jumping over an override, and we have to support all this. It is tricky. But we handle this all right, hopefully now. And we also handle the simpler cases. We just record those real credentials. Currently we also record some information about the comp, pretty limited one, pretty limited set of information. And as part of credentials, we do record one namespace pointer, so some trivial or extensive container breakouts could be detected this way. They do not try to be more selective in what they do. Like I mentioned, there are many cases when we do need to update our shadow data for the task. It's passing through various calls. It's creating and terminating a task. And I mentioned that we do want to verify task credentials just before they would be used, just before they actually matter a lot. For example, when there is a call to open a file, this is the moment, one of them, when we do verify integrity of this task, that the credentials it has are still matching what we have in our shadow task entry. There is still a time window between our check and us returning back to this open call and letting it proceed, but it is a much smaller window than it would have been otherwise if we didn't try to time things this way. We do not actually hook open specifically. It is too specific, unnecessarily too specific, and we would have needed to hook lots of calls if we did that. We instead hook internal kernel functions like capable, which is called basically to check privileges, and generic permission for the simpler cases not involving capabilities. We also verify when we do this just-in-time check that the control flow reaching this place in the kernel, that it looks sane. This is poor man's, as we officially call it, control flow integrity enforcement technology, a really simple one. But we do unwin the stack and look at the stack frames and check the addresses are in the kernel. We do maintain this data per task, and it is kind of a database. We have to index it by some key. We used to index by PID, now we have switched to indexing by a hash of the current task pointer, the address of task struct. And by the way, there are various concerns here about timing leaks, but things seem quite fine, at least compared to what the kernel does. There was this great talk yesterday I really liked about timing leaks with hash tables. We do have a hash table here, yeah. But no user input reaches it, only kernel internal addresses. And we optimized the performance and scalability of this solution a lot. First, for version 0.8, we had Pharonix benchmarks. Michael Larabelle ran those and published on the website. We were unhappy with performance impact, so we quickly optimized things, and here I ran, and results were much better. And now there is yet another round of those updates. Sultan, he joined CIQ recently, and CIQ allowed him to spend quite some time improving LKRG. And he implemented a new locking mechanism for this data. basically we have now lockless reads, so scalability should be even better, but on small systems we do not notice the difference. Mostly the previous solution was already good enough. Maybe on really large service like 200 cores or something and 1,000 of running tasks should be difference. And finally, a feature that doesn't fall under any other category, we block some kernel interface that is used to run user mode programs, and basically it is quite usable for attacks. There are a couple of examples here, and by the way, the CV is still unfixed in upstream Red Hat Enterprise Linux 9 and 10, which is ridiculous, and you can still dump shadow in this way. And I actually wrote a blog for CIQ on the blog website with ASCII numeric codings of how you do this hash dumping and how you crack them, then the passwords from there just works. Anyway, on a more serious note, functionality is actually needed on you could do without it, but the distros they currently assume that it is present, so it isn't so easy to remove. And instead of removing, we use an allow list by default with hard-coded full path names to allowed programs. So a kernel exploit cannot just run a program of their choosing. Then we have a configuration of LKRG. It is model parameters and also runtime configuration through this control. And we keep the stuff on a read-only page. We switch it to read-only after we have made modifications. And you issue this control to make changes, and it goes to read-write and again read-only. And we also host a few other critical things for LKRG in there. And we do have this control named hide, which would hide LKRG itself, and I'll hopefully have a little bit of time to mention it a bit later. We also test that key probes, which is what we use for hooking, that they actually work. An important test, as it turns out. And we have remote login. Why do we have it? Here are some reasons why. But the only real competing solution that is seriously worth comparing against is the simple net console thing inside the kernel itself, which has no encryption and which requires you to specify a hardware MAC address for Ethernet. So useful for debugging, not so much over the internet, although you can get it to work over the internet, as I mentioned on that slide. And what we decided to implement, I actually gave a separate talk on the remote login. You can see many slides about this decision-making process on the Openwall website, but here it's a condensed version, just the outcome of the decision-making. We decided to use noise protocol. One of the instantiations of it similar. The key exchange is actually the same kind that WireGuard, the kernel, not only kernel uses, and that WhatsApp Messenger uses. But for actual encryption of the data, we use Cipher that is different, that is optimized to be tiny, but it's also fast. So that's what we have, and we use TCP, and we do actually one-way communication. And one-way communication, it enables us to have a write-only socket and not to worry about creating extra remote attack surface for the kernel. We could have better security for the communication by having a two-way proper handshake, but then we would be open to potential attacks on this data processing from the remote. We did not want that. So for now, it's really simple. And the receiving and logging, it's in a user space program. And effectiveness of LKRG, it was tested independently by someone writing their master's thesis, and there we see efficiency effectiveness detected 8 out of 9 of what it could potentially detect. So kernel rootkits, it doesn't detect, that it doesn't try, it shouldn't detect, it would be a false positive if detected user space rootkit currently. And the only one it didn't detect, it wasn't exactly a rootkit, it was a keylogger. Also exploits, it does stop exploits that it is supposed to stop and that haven't been specifically adapted to bypass LKRG. There are several examples here, and there were more. Basically, you can see tweets, people posting like screenshots, this CV, this exploit under Debian, not CV is listed here, some other one is also caught. But then there are examples that wouldn't be caught when you attack user space from the kernel directly, bypass compromising kernel integrity and compromise user space integrity through kernel vulnerability, and the kernel stays intact, it's currently out of scope for LKRG. And then there are bypasses. So far they exist in the form of modified exploits that previously didn't have bypass, so those exploits previously were caught by LKRG as exploits were initially written, but they then were extended to also bypass LKRG in different ways. And the most recent one, it actually finds and patches LKRG itself. Our code, our checks basically are patched out, and this is done, I think, from an extended ROP chain. So complexity grew quite a bit, and the required knowledge of addresses, it also grew significantly. The exploit has to know addresses not only of the kernel, but also of LKRG where it is located. So we can improve things by hiding LKRG, by hiding kernel symbol addresses. This is something we should work on after 1.0. There is already, and had been at the time, this hides is control, which actually stopped this specific bypasses implemented by Alexander. But it is not set by default, so by default the bypass work. There are some drawbacks in basically hiding LKRG. It's inconvenient. You load it, you hide it, and then you first have to unhide it. More difficult to manage. And we do support a wide range of kernel versions. I think it's spanning more than a decade, maybe even 15 years. I don't recall exactly when 3.10 base version was released. It's still maintained as a branch in Red Hat Enterprise Linux 7. Well, officially it is past end of life since last year, but there are still maintained forks of this distro, including CIQ. We have so-called bridge. It's a product to bridge transition from CentOS 7 to 8 and 9 Enterprise Linux. And meanwhile, long-term support for 7 still exists, and we support those kernels, LKRG loads in them, and works fine. And we support 4 architectures. All 4 are tested in our continuous integration setup on GitHub. We run in Chemo. And we support latest mainline kernels. So our continuous integration setup again had tested just a few days before this talk. It came out this RC4 release candidate 4 of 6.17, and it got tested automatically. It works. So what we do is actually quite invasive integration into the kernel. We hook functions that we were not supposed to hook. Not only hook, even to access them in any way at all. The symbols are not exported. So the compiler is free to do various things like totally throw away such symbols, duplicate them, inline them, do weird things. So we have to be careful. We have to choose which of the non-exported symbols we can actually use this way. And it is also difficult to call functions this way. One issue is with hooking, and the other with calling. When we hook, we may end up hooking just one duplicate of a function if the compiler decided to duplicate and specialize, for example. And when we are calling, we can bump into control flow integrity enforcement by CPU or compilers that was used to build the kernel, and LKRG ideally is built the same. For 1.0, I implemented a bypass of Intel control flow enforcement technology in direct branch tracking. This is only forward edge CFI. They also have backwards edge protection through shadow stack. But the Linux kernel doesn't use shadow stack. It supports enabling shadow stacks for user space use, but the kernel itself does not enable shadow stacks for its own use yet. And I think there are no current plans. So it only does the forward edge thing, and we bypass it basically by using the reverse edge instead, and we use push and read on x86. So we put the address on the stack, and then we return to the function that we actually want to call, and it works. And similar tricks work to also bypass software-based CFI implementation in Clang. We do not officially support Clang, so there may be other issues with Clang builds, but this one hurdle we took care of. I think it should work. And per user reports, they passed this step and they reporting other issues with Clang now. But with GCC, things are stable. With Clang, your mileage may vary. Some people report success, some various issues. The typical issues, bugs in LKRG is mismatched assumptions. Sometimes it is really difficult to figure out what the kernel can actually do and what it cannot do, what is allowed state, what is not allowed, what combinations of states are allowed when. So race conditions, what locking conventions should be there, how we can adapt to this. And this, for a trivial example, it was also compared to most other mismatches. This one was trivial. We overlooked introduction of an extra seccomp mode that is kernel internal. It is not available from user space. And because of this, we had false positive, very rare false positive. When a process was terminating, it could also briefly see corruption through LKRG. It would be done anyway, so no big deal, but false detection anyway. And it's fixed now, of course. And by the way, to fix it correctly, I had to write a lengthy check of kernel versions, not only of the mainline kernel version where the change was introduced, but also, I think, 4 stable branch versions I checked for backports, and I had to spend time finding those. And there was one really bad bug in 2020, which was a near miss. Luckily, no impact beyond crashing the systems by a user, but we had to spend time evaluating whether there was possibly worse impact, and we determined that there wasn't. But anyway, there is risk. Most of the processing we do isn't on untrusted input in the usual sense. It may be untrusted under our different threat model when the kernel can be already partially compromised. But in that case, we are not making things worse, at least even if we have a bug. But some untrusted input for real, it also exists, and the risk of us introducing vulnerabilities exists. So 7 years so far, and no one found or at least reported anything really bad, but that's how it is. And I did mention our continuous integration, so we test for architectures under QEMU. Well, x86-64 we just run, except when we do an image build, so we build like almost natively on GitHub Actions, but then we have to boot up. And we support, for example, a range of Ubuntu versions we test, and we also test with latest mainline kernels, as I mentioned. And we build test for even more systems. This has helped us save time on development and find bugs much earlier. It was really helpful to have this continuous integration. And there is support in distributions packaging, and in particular at CIQ we also have packages for the free enterprise Linux rebuild distros like Rocky Linux, and can be reusable on Alma Linux or on paid RHEL. And we also have our own hardened product that actually has LKRG integrated, enabled by default, and signed for secure boot. And there is performance impact, obviously, from the many things that LKRG does, and it was measured to be about 2.5% as a geometric mean of many tests. It can mean various things. It can mean, for example, that 10 tests are not impacted at all, and one is a lot slower. And there are such cases. And some tests actually show speed up. It is not reasonable, but it's basically a random fluctuation. So, in real world, it is reasonable. It is like computer science, you run experiments, and results can be sometimes unexpected. So, in 1.0, we have lots of changes, including support for newer kernels, and we reduce the performance overhead, and we actually also shrink the code base by 2,500 lines. I did this. I'm good at removing the code while hopefully keeping the protections, and Adam is adding protections. So that's how we manage. And for potential future, we try to make LKRG even more mature, and we want to improve the coding style to switch towards Linux kernel users. We already use this coding style for some new contributions. For example, my implementation of the remote login, it already uses Linux kernel coding style. But most of the code base still uses the style that Adam prefers or preferred for this project initially. Now he agrees that it would be better for the community to have consistent style that is common for Linux kernel code. And we want to improve self-protection more. We want to add hiding, as I mentioned. We want to reduce attack surface more. In particular, I really worry about namespaces. Many of the exploits, if you look at really impactful local privilege escalation exploits for Linux, about half of them could be abusing unprivileged access to namespaces. We could harden this in some ways. Then there is a new direction potential to also add protection for user space against attacks within user space, and general anomaly detection also including user space. And there are other ideas about protecting from higher privilege level. As I understand, this is actually done on some other systems like Windows and iOS. And this on the surface this is a good idea, and Adam really wants to implement this. He actually has a text file on his personal website about how he would go about adding this to LKRG. And there is actually a fork of LKRG unreleased by a certain company that implemented this for a certain mobile device for a certain government with LKRG and TE on ARM, I think. But from my perspective, there is also a problem, because the kernel would remain the leader of this transaction anyway, because we do not want any false positive, and this means consistency, and this means locking, and the kernel will hold locks that the hypervisor will have to wait on. So not really moving from this privilege level, not fully. And for eBPF, we actually had a fork of LKRG that did some eBPF protection, including allow listing of programs. Adam wrote this, but we haven't released yet. We don't know about the future exactly. So that's it. I think I'm a bit over time for the demo, but I would like to show if there is a moment still to... So we have this system where the LKRG logger is set up. It is a package built for Enterprise Linux 8.10. It's built under SIG security, so the security name for Rocky Linux, but actually installed on Alma Linux 8.10, also to demonstrate compatibility and reuse of those packages. And the repository is connected, package installed, and here we see one of the log files that is being written. And I have another system. The first one is Amsterdam, and this one is in New York, where we have this old vulnerable kernel, and we have an exploit here. And this is an exploit by Chompy, to give credit where it's due. And let me see what we have currently. We have some stale records in there. I was running it before. And yeah, so we have those as stale records. And I can actually show you decoded timestamps. Those are full timestamps, like for forensics, to determine things like clock drift. But we do have this processing tool, which can give us pretty timestamps. This was 3 days ago I was testing. Let me leave this at it, and I run the exploit in U. And it got killed when it was supposed to give root. But let us see here. Oops, somehow no new records. That's unexpected. I don't know what might have happened. So it isn't actually connected here. Okay, let's see here. So okay, but it is hard to tell when it is. By the way, this system has been up for quite a while. And let me see. Okay. And then I can run this exploit again while we do not have protection. Okay, that's not it. Okay. It will probably succeed now. Yeah, so it does. And let me load LKRG again. So I also show you how you specify the server address and a public key. Let me see how it's loaded. Okay, so the new messages are these ones now. Okay, let me see what's here. Also propagated to here. And now let's try exploiting again. And let's see what's here. Okay, so it logs this event now. I'm surprised why the connection somehow wasn't up. I don't know. Maybe I just inserted LKRG without specifying the mode. I was testing stuff. It was during the 1.0 release process. As I have shown, the system has been up for over a year, and it was basically, it kept this connection stable during this time. It isn't like it disconnects arbitrarily, and there is logic to reconnect actually. So I think I simply had LKRG loaded without remote login, and I forgot. So that's it. And if there are any questions, but I don't know if there is time for them. So